The traditional way to simulate polymers is to think about them directly in terms of real particles bouncing around. This video is meant to describe how we can derive a far more computationally efficient statistical field theory for polymers. It's meant as an overview, so if you want more information, see the papers linked in the description. The simplest polymer, that I can think of anyway, is polyethylene, a simple chain of carbon atoms shown here in red, bonded to each other forming the backbone of the polymer, and each carbon atom is bonded to 2 hydrogen atoms. For a more interesting example, this is polystyrene, where each monomer also includes a phenyl group, or benzene ring, that I've colored in yellow. There are many other examples forming all plastics, as well as biological molecules like proteins, carbohydrates, lipids, DNA, and RNA. From here, if we want to know how polymers behave, we can simply, start from here and plug in what we know about how atoms interact with each other. We know how all the atoms are bonded together. We know the bond lengths, as well as the energetic costs associated with deviating from those bond lengths. We also know the bond angles. For example, carbon atoms tend to form a tetrahedral arrangement with an angle of 109.5 degrees between bonds. These bonds can move a little, but we know the energy functions associated with deviating from those equilibrium angles. We also know how non-bonded interactions work. That is, we know the energy is a function of the distance between atoms, and thus the forces they exert on each other. There are also dihedral angles that I've not included here, but once again, they're known. I've left off charges here, but we know how forces associated with charges work. There's some nuance to this. These energy functions can be difficult to obtain, and precise values depend on the environments that the atoms find themselves in, and they can take a lot of work to find precisely. But for the most part, for practical purposes, these energy functions and relative interaction strengths are known, or at least well approximated. So what do we do from here? Well, if you know the energy functions and therefore the forces, it's just a matter of setting up the system and solving Newton's equations. Calculate the forces, step the precision and the velocities forward in time a little bit, and repeat over and over again. This is a simulation of a single molecule of polystyrene block polyethylene. That is, a polymer where a polystyrene molecule is bonded to a polyethylene molecule, and here it's just floating around in a vacuum. I started it with the polymer fully stretched out and just let it run. There's something kind of viscerally satisfying about watching molecular dynamics simulations, watching every single atom just move around and do its thing. It's kind of nice to see all these little atomic details, and feel like you're peering into the atomic world. You almost forget that this is just a mathematical abstraction. Molecular dynamics simulations are particularly useful in biological systems. For example, this calculation, where a ubiquitin molecule is being pulled on to see how it unravels. Seeing how proteins fold or unfold is a huge topic in biophysics. I'm interested in polymers, biological and otherwise, but molecular dynamics is a powerful technique applicable to many systems, from proteins to annealing metals. Here's an MD simulation I did of 8 molecules of Buckminster fullerene, that is 8 buckyballs just bouncing around in a box. MD is so general and so conceptually simple that your imagination is your limit. Well, kind of. There are some difficulties. For one thing, setting up these simulations, even if conceptually simple, is not that easy depending on the system you're looking at. But that's minor. If tedium stopped a scientist, we'd never get anything done. The real problem is the time and computer resources involved. One interest of mine is phase separation in polymeric systems such as block copolymers. I can easily set up a system of a melt of polystyrene block polyethylene and run a simulation close to where experiments see it forming layers. This is an example of such a run. Rather than seeing layers, however, what I get is frustration and boredom as I stare at a seemingly unchanging system. I suspect that I would eventually get layers, as that's what's seen in experiments, but I'm just not willing to wait that long. The systems that I've shown are tiny and run for very short times. Real-world problems are a bit more complicated, involving orders of magnitude larger systems and longer times. The mesoscopic polymer behavior that I'm more interested in happens on timescales to the far right of this figure, far beyond what one would use MD for. In order to go further, we have to find a faster way of conducting simulations. In the calculations so far, we've considered each atom individually. For systems with a lot of atoms, this gets computationally expensive. Rather than doing all atom molecular dynamics simulations, we can simplify the problem by coarse-graining over sets of atoms. Rather than considering interactions between individual atoms, we can consider effective interactions between groups of atoms. In this case, I've replaced a monomer by a single bead. Rather than looking at, say, polystyrene block polyethylene as we did before, we can replace monomers by beads, and replace the interactions between monomers with ones that ideally would mimic the effective interactions between the actual monomers, and then we can run the simulation and see what happens. This simulation qualitatively reproduces the behavior seen in block copolymers, but I didn't carefully choose the interaction strength to reproduce those of polystyrene block polyethylene. In order to get the simulation to occur in a reasonable time, that is, a time that I'm actually willing to wait for, I had to fiddle with the interaction strengths, and even then it was kind of annoying to wait for it to run. But if we're going to abstract out the atomic details, creating a model that needs to be mapped onto the real thing anyway, we can do a better job. So let's try something else. The next part of this video is going to get a little bit more mathematical. If you want to skip over the math, you can fast forward, or there's another version of this video where I give a more heuristic approach to the formation of a field theory. What we're doing here is statistical mechanics. We're looking at the statistical behavior of a set of objects interacting with each other. In statistical mechanics, there's a quantity called the partition function. The partition function is a sum over the Boltzmann weights of all possible states of the system. It's basically the holy grail of statistical mechanics. If you know the partition function, you've solved the system. You know everything you want to know about the system. Physical observables correspond to derivatives of the partition function. Molecular dynamics and other simulation techniques can be thought of as methods to enumerate the states that a system can occupy, and an approximate way to estimate the partition function or its derivatives. Questions about the equilibrium behavior of polymers, or for example protein folding, are essentially looking for likely configurations. The connection between this and dynamics like transitional pathways gets a little bit abstract, so I'll leave that for now. The point is, we want to find the partition function. For the case of our polymers, the partition function is an integral over all possible configurations of all polymers in the system. The energy function is the sum of the non-bonded two-particle interactions for all particles, as well as the bonded interactions. Different polymer models have different forms for these interactions, so I'll leave the form of the interactions for now. Also note that I've left off self-interactions and other factors that just contribute to a multiplicative factor and it don't really matter. It turns out to be easier to write the partition function in terms of an integral over the instantaneous concentration of polymer particles. I've labeled this instantaneous concentration as rho hat. Now I'll just shove the bonded interactions into the term representing particle configurations. This is just a mathematical rearrangement, but conceptually, it corresponds to thinking about integrating over the Boltzmann weights, but with each conformation weighted by its likelihood irrespective of the non-bonded interactions. The next few steps constitute a little bit of mathemagic. If you're not interested, just fast forward a bit. I'm going to use a functional delta function, which is kind of like an infinite dimensional version of the Dirac delta function. Its argument is a function, and its value is 0 unless that function is 0 everywhere. So in the example, delta rho minus rho hat, rho and rho hat are both functions, and the functional delta function is 0 unless both functions are identical. Just like a regular delta function, it has a shifting property. And that is, if you perform a functional integral over this functional delta function times f of rho, integrated over rho, this is equal to f of rho hat. You can switch the rhos and the rho hats in the f as much as you want. Just like you can write a regular delta function in Fourier space as an integral over I times, say, k dot x, we can write the functional delta function as a functional integral over e to the I integral over the product of two functions. Also, just like a regular delta function, if we multiply our partition function by the functional delta function and integrate over it, this doesn't change anything. Next, let's insert the integral form of the delta function from above. Using the shifting property, we can replace the instantaneous concentrations rho hat in the pairwise interactions with rhos, and that's kind of where the fun begins. The only part of this integral that depends on the instantaneous concentration rho hat, and therefore that depend on the particle positions r alpha, is the w term. So we can write it like this, and separate out the part that depends explicitly on the particle configurations. This term, which I've labeled Q, can be interpreted as the partition function for a polymer that doesn't interact with other particles, but is subject to the function W. I'll address the meaning of W shortly, as well as the seemingly nonsensical phrase subject to W. Q alpha is the partition function for the alpha-th polymer. If all the polymers are the same, then the product over n polymers simply raises the partition function to the power of n. What we're left with is a partition function given by a functional integral over these fields, ρ and w, of an effective Hamiltonian h, which is a function of ρ and w, and a single chain partition function q. This is the central result that we were looking for, a partition function for a polymeric system written in terms of integrals over fluctuating fields. This function forms the basis for a statistical field theory for polymers. So now that we have these fancy functions, what are ρ and w, and how do we actually evaluate the partition function? Ρ can be identified with a fluctuating concentration or particle number density. You can see this because the functional integral that we introduced constrained it to ρ hat, the instantaneous particle density. W is a field representing the fluctuating inhomogeneous chemical potential. The astute viewer might have noticed that it was introduced conjugate to the concentration. It turns out that we don't actually need to do both of these functional integrals over ρ and w. The partition function can be given just in terms of an integral over w. I'll take the usual cop-out of actually deriving it and say that it's an exercise left for the viewer. The derivation is in Chapter 4 of Fredrickson if you're interested, so you can just check that out. Note also that this is a canonical partition function. That is, the derivation assumes a fixed number of particles, fixed volume, and fixed temperature for the system, but it is derivable in different ensembles. Deriving in different ensembles turns out to just change the log Q term. If we want to consider systems containing more than one chemical species, it's not too difficult. We just calculate the concentration of each species, and we insert a field corresponding to each one. This can take the form of two different monomers, in this case A and a B monomer. This is kind of like the polystyrene and polyethylene systems that I showed earlier. There are two things left to discuss for this description to be complete: the particular polymer model being used, and the form for the pairwise interactions, U. I'll address the model first. If you're dealing with short polymers, every monomer is important, and you may want to include monomeric or even atomic details. As polymers get longer, their average properties become more important, and the fine details less so. You can think of them as sets of beads as shown here, but for practical purposes, the beads likely don't even matter, and you can think of them as somewhat stiff strings through space, of some set length and some set stiffness. When they get really long, even the stiffness of the bond angles doesn't really matter, and you can think of them as fully flexible strings just floating around in space. Their path is basically just a random walk. When they get really long, you can think of them like fractal strings. The behavior of individual monomers is long past relevant. Even the behavior of small regions can be averaged out, and you get basically a big stretchy string. This is a Gaussian chain model. The details of different types of polymer models is an interesting topic, but beyond the scope here, and I've glossed over a lot of details. The point is that the Gaussian chain model, although strictly only accurate in the long chain limit, is good enough for most practical purposes, which makes it the model of choice for a lot of people and a lot of polymer problems. Parameterizing the Gaussian chain by S, so S equals 0 at one end and S equals 1 at the other, we can write a concentration like so, as an integral over the chain. I've scaled it by the average monomer concentration ρ0. One useful quantity for the Gaussian chain is the average end-to-end distance r0. We can chop the Gaussian chain into n pieces or segments of length a. A Gaussian chain is a random walk of those segments, and thus has an end-to-end average distance of the segment length a times the square root of n. The Gaussian chain, however, is a self-similar fractal. Each of these segments is itself a random walk, and a is the average end-to-end distance of the segment. If this confuses you, don't worry about it. The Gaussian chain confuses a lot of people. The point is that the behavior is close enough to the behavior of real polymers once they're long enough, and it has the properties shown here. To find the statistical behavior of the chain, we're interested in a function called the propagator, or partial partition function. The propagator, q of r and s, gives the partition function for the portion of the chain from 0 to s, given that the monomer at polymer position s is fixed at spatial position r. The propagator follows this diffusion equation. So given some initial condition for the propagator, which is defined by your problem, you can use this diffusion equation to find the partition function for any portion of the chain. When we want to find the partition function for the whole chain q that we saw earlier, we need a back propagator that I've labeled q dagger. It's basically the same as the forward propagator q, but it's found by integrating from the other end. This function for a capital Q may look weird because there's an s dependence in the propagator, but it just disappears. The partition function, capital Q, is the same regardless of the S that's used. Once we've found the forward and back propagators, we can find the concentration by integrating over their product, scaled by the partition function. There's some subtlety here because you get different scalings in different ensembles. This scaling is just for the canonical ensemble. Also note that if you want to find the concentrations for different portions of the chain, not the whole thing, just change the limits of the integral. If the chain contains different types of monomers, for example an A-type and a B-type like before, with corresponding fields WA and WB, or more generally W-gamma, then we just have to modify the diffusion equation so that each part of the chain fields its corresponding field. The concentration of each portion of the chain is then found simply by restricting the integral to the corresponding part of the polymer. The next step is to define a pairwise potential. We could in principle use the Lennard-Jones potential or whatever else from earlier, but there are simpler choices that we can implement without losing much. We'll take the simple approach of making the potential local, so the potential just looks like a delta function. This approximation works well when the polymer is long, so the length scale that you're looking at is large compared to the range of two-particle interactions. I'll define this pairwise energy in terms of a mixing energy. Think of it like setting a baseline energy U equals 0 when all the A's are with A's and when all the B's are with B's, and the energy is just the excess over this that occurs when A's mix with B's. The physics doesn't change when we add a constant to the energy, so we can set U equals 0 wherever we want, in this case at this baseline energy. This 1 minus Kronecker delta Ij picks out the interactions between unlike monomers. The strength of these AB interactions is characterized by the Flory-Huggins interaction parameter chi. In systems with more than two components, there's a separate chi parameter for each pair of monomer types. And one last thing that I'll just gloss over. In what follows, I assume that the polymer fluid is incompressible. That is, it has a constant total concentration. This involves cramming in yet another functional delta function and going through the same process as before. Combining all of that and rearranging a little, we can write our statistical field theory for a fluid of AB diblock copolymers like this. The partition function is a functional integral over the Boltzmann weight of an effective Hamiltonian, which is given by an integral over two fields and a partition function for a single polymer in those fields. The partition function can be found using the propagator method shown earlier, as can the concentrations if you're into that kind of thing. Rather than writing WA and WB, which act on A and B monomer concentrations, I've written the fields as a composition field, W-, that couples to the difference in A and B monomer concentrations, and W+, a pressure field that couples to the total concentration. Now it's just a matter of calculating the integrals in order to determine the behavior. There is a number of approaches to this, most notably Monte Carlo simulations and Langevin dynamics simulations. I went through these derivations a bit quickly and glossed over the introduction of two fields, and especially the introduction of W- and W+, so you'll be forgiven for not noticing, but if you go through carefully, you may notice that the fields W- and W+ are not exactly real. Well, W- is, but W+ is purely imaginary. This renders the Hamiltonian complex, which creates all kinds of issues. If you try to plug this into standard Monte Carlo, you end up with complex probabilities, which don't exactly make any sense. You can get around this by approximating W+ using mean field theory in a way that I'll discuss shortly, and sampling W- using standard Metropolis Monte Carlo. It turns out that it works pretty well for many practical purposes. The procedure does not, however, scale very well with system size, and there are faster approaches. We can also do Langevin dynamic simulations. This entails deriving time dependence of the fields from the Hamiltonian, yielding complex Langevin field-theoretic simulations. There are some technical challenges that I won't get into, but if you want more details, there are links in the description. Many of these difficulties can be overcome by, as before, approximating W+ using its mean field value, producing real Langevin field-theoretic simulations. Once again, I'll describe what this mean field business is all about shortly. This is an approximation, so it's less accurate, but in many cases the cost is small and it buys us a lot in terms of simulation power. Once again, links are in the description, particularly Matson 2020. This is the result of a real Langevin field-theoretic simulation. It's comparable to the layer-forming one that I showed earlier, except that the system is much larger and I didn't have to crank up the interaction strength to get it to actually form layers in a reasonable time. The parameters are close to the order-disorder transition. As before, it phase separates quickly into A and B domains, but they form this disordered interpenetrating lattice. After a little while, some layers start to nucleate and grow to engulf the system. Soon all we have is fluctuating layers. The system has some average configuration, and it's fluctuating about that configuration, in this case, a layered configuration. What's happening is that the Hamiltonian is sharply peaked around one configuration, W of R, corresponding to the lamellar or layered system, and the system fluctuates around that configuration. This means that the partition function is dominated by contributions around this peak, where the peak itself corresponds to the single most likely configuration. The more sharply peaked the Hamiltonian is, the more dominant this contribution will be, and the less the system will fluctuate around this peak, and therefore the less the fluctuations will matter. To make things a bit clearer, I'll bring the number of polymers, lowercase n, over to the right. The larger the number of polymers is, the more sharply peaked the Hamiltonian is. This makes sense. For bigger systems, if we're averaging over more polymers, the average fluctuation away from the most likely state is smaller. But let's say we have systems with polymers of different lengths, that is, different capital N's. The question is, does this affect the fluctuations? Let's consider a system of polymers with length or polymerization index capital N, in a volume given in terms of the end-to-end distance R0. R0 is the natural length scale for a Gaussian chain, and it dictates the size of the structures formed. If the system wants to, say, form layers, a system of length 10 R0 will form the same number of layers regardless of the length of the polymer, all else being equal. Rearranging this expression and plugging in the definitions of the quantities shown earlier, we get that lowercase n equals the square root of this new quantity n bar times the volume in units of R0. This quantity n bar, called the invariant polymerization index, sets the strength of fluctuations. Unlike capital N, which is arbitrary, you can chop up the polymer into however many pieces you want, n bar is not arbitrary. A given polymer has a specific n bar. Physically, n bar tells us the degree to which polymers overlap. Larger n bar means each polymer is sampling more of the system, meaning that the environment that the polymer experiences is closer to the average environment, i.e., fluctuations far from the average are less likely. This is the physical origin of the more sharply peaked Hamiltonian as n bar increases, and the fact that as polymers get long, fluctuations get small. In fact, as n bar goes to infinity, the only contribution to the partition function that matters corresponds to the single most likely configuration. To put this in perhaps a more intuitive way, if the polymers are infinitely long, they perfectly sample the field. If you put an infinite set of particles in a potential, their distribution will exactly match the probability distribution predicted from the potential. At the same time, the field comes from the particle distributions, so if you have the particle distributions, you can calculate the field. This gives us a set of self-consistent equations forming the basis of self-consistent field theory. Self-consistent field theory is a mean field theory and is only strictly correct in the limit of infinitely long polymers, but it turns out to do a very good job for many circumstances. It's also way faster and simpler than full-blown simulations. Self-consistent field theory is able to predict the structures seen in experiments. The examples shown here are for block copolymers, but this is just one of many applications for SCFT. SCFT even predicts the topology of the phase diagram almost perfectly. You may notice that the phase diagram from theory and experiment match pretty well near the top, but the bottom looks a little different. Self-consistent field theory predicts the disordered phase transitions to spherical phases before it goes into the other phases, whereas experiments find that the phase boundary between all of these phases and disorder is direct. The transition between order and disorder is also pushed up to higher chi-n as compared with theory. These differences come about because SCFT looks at the single most likely configuration and ignores fluctuations. When fluctuations are included, the theoretical phase diagram matches even more closely with the topology seen in experiments. This particular theoretical phase diagram was calculated using complex Langevin simulations, and for technical reasons, used slightly different assumptions that went into the previous SCFT calculation. I'll leave you with this mesmerizing simulation of a mixture of two polymers of different types. I hope you enjoyed this exploration of polymer field theories. This way of looking at polymeric systems allows for fast, efficient, and yet accurate ways of describing and simulating polymers, and offers insight into not only how polymers behave, but why they behave that way. The model that I've presented is approximate, but only at the level of the polymer model itself, i.e. the Gaussian chain model in this case, and interactions between monomers. The conversion to a field-based model is mathematically exact. Even so, the approximations that I used miss some microscopic details that you would see in fully atomic theories. But for many systems, this cost is small, and it buys us the computational efficiency needed to explore these large complex systems. If you enjoyed this video, check out the other videos about my work, or better yet, the papers. Anyway, thanks for watching and listening.